Good morning. My name is Dr. Melnizer. I'm going to talk to you today about light or electromagnetic waves. Electromagnetic waves are important to understand because they're primarily a means of communication with the world around us. They're not only the light that we see and use to experience sight in the world around us, but it's also the method we heat up food with microwaves, keep it warm with infrared light, tanning beds with ultraviolet light, the means of communication through cell phones, through both radio waves and microwaves, the latter also used for Wi-Fi, and understanding how we use gamma rays and X-rays for medical science. You'll succeed if you can tell me the 7 different types of light and what diffraction, refraction, and reflection are. Light is electromagnetic radiation. It's released by atoms. When an atom gets really excited, it's going to release it in the form of visible light, ultraviolet light, microwaves, radio waves. Electromagnetic waves are both visible and invisible. In fact, most of it we can't see. They're a transverse wave and a form of energy. Light is different than sound, since light is a transverse wave rather than a longitudinal wave. Light doesn't need anything to move through. Sound wave does require something to move through. Light is slowed by the media it travels through, while sound travels better in dense media. Light is created when an atom absorbs energy. If it vibrates fast enough, the electrons get knocked from one orbit to another. And the atom's like, wait, I'm unstable. I'm going to grab that electron and pull it back. And when it's pulled back, it shakes and it vibrates in a waveform. And that waveform is the light. By the same token, if that light hits an atom, it can knock an electron from a normal state to that higher state too. That is how light is both created and absorbed. The speed of light. The speed of light is the speed limit of the universe. Nothing can travel faster than the speed of light while operating in the universe around us as if it has mass. The speed of light is exactly 299,792,458 meters per second. That is way too complicated to remember, so most scientists just use 3 times 10 to the 8 or 300 million meters per second. We also abbreviate that with the letter C. Now, light slows down ever so slightly when it's traveling through a vacuum like space until it hits the Earth. It's going to be moving about 88,000 kilometers per second slower, but it still rounds up to 300 million meters per second, 3 times 10 to the 8th power. The speed of light slows down much more in water. It's going to travel to 75% of its speed, or 2.25 times 10 to the 8th meters per second, or 225 million meters per second. Finally, the speed of light when it hits a solid, and a clear solid, something it can travel through easily, like diamond, it's going to slow down even more, 1.2 times 10 to the 8th meters per second, or 120 million meters per second. Now, when we talk about light, we typically talk about its wavelength. Larger wavelengths typically travel long distances and in a stable form, but they have a lower amount of energy in the impact. They also typically transfer that energy in heat. Whereas lower wavelengths have high frequencies, they have a lot of energy, and they can actually cause chemical changes when they hit something. That's why you can be bombarded by radio waves all day, and if you hit by a lot of them, you'll get hot, but you won't actually feel any changes. Whereas if you're hit by things like ultraviolet light or X-rays or gamma rays, you can get cancer, because when those things are actually hitting your cells, they can cause damage and chemical changes inside of you. Here is a scale of the types of electromagnetic radiation. The largest, which is as tall as some buildings, or even taller at a kilometer, 10 to the third power, or 1,000 meters, down to a few meters are radio wave size wavelengths. Smaller, we have to the size of humans to butterflies are microwaves. These are the microwaves that both heat your food, and it is the 4 and 5G transmissions on a cell phone. It is also the type of transmission used on a wireless router. Smaller than that, from the size of a butterfly to the head of a pin, is infrared light. This is the light in heat lamps that keep food warm. In a tiny, tiny sliver of the spectrum, half of a millimeter times 10 to the 6, or 400 to 780 nanometers, is visible light. This little fraction is all of the colors of the rainbow that you can see. When we start going smaller, ultraviolet means higher frequency than violet. It goes down to molecules in size. And these molecules in size are ultraviolet. And by the way, when they hit the molecule, they will cause a chemical reaction. That's why it can't penetrate your skin. X-rays can shoot through you and they will cause chemical reactions. That's why they all have the big warning cancer sign. And gamma rays will shoot through anything. It'll shoot through entire atoms. However, it hits the nucleus, it causes changes. It is very, very tiny stuff. Radio waves, biggest form of electromagnetic radiation, usually wavelengths between 1 millimeter and 100 kilometers, used for transmission of information. Microwaves, between 1 meter and 1 millimeter, commonly used to heat things, just like the microwave. By the way that works, you'll see a metal panel in the side of the microwave. It's going to release microwave light. By the way, the wire mesh you see in front of the glass catches that electricity. And by the way, if that light hits something metal, it turns into electricity, much like a solar panel does. And that's why it's dangerous to put metal things in the microwave. If it's left in long enough, it won't cause things to explode. It'll just cause the charge to build up high enough, cause a giant spark, much like a lightning bolt, to arc from your food to the side wall of the microwave and break the microwave, possibly start a fire. Using the same type of waves, microwave transmitters, the small circular disc-looking things that are attached to the side of radio towers, will transmit high information microwave 4 or 5G to have your cell phone work. Infrared light. Infrared light is the light that your body produces. It's heat light. When you put on clothing and feel hot, what you're actually feeling is the light bouncing off of your clothing and back into you, warming you. That's why you wear heavy, thick clothing in winter and thin clothing in summer. Infrared is between 700 nanometers and 1 millimeter. By the way, since it is below the frequency of red, we call it infrared. Visible light, between 740 and 380 to 400 nanometers, color of the rainbow. Most important thing, highest wavelength is red at 700 to 740 nanometers. Violet or purple is 380 to 450 nanometers. Ultraviolet, because the frequency is higher than violet, it is ultraviolet. This is the type of energy we typically use for treatment of some types of liver problems, especially in babies, or in the case of tanning beds. It is between 10 nanometers and 380 nanometers, so very tiny, tiny beams. They can't usually get past skin. They can cause skin cancer, but because of the high energy amount, it can cause some chemical changes. This is the reason some chemicals left out in sunlight will go bad. This is why things change color when left in sunlight. Also, it is why there's tiny tanning beds in hospitals. They're not so baby can get a tan. It's in case baby has a liver problem. The ultraviolet light can cause certain liver chemicals in the blood to react out so that kiddo will be safe and not have something which will hurt him inside him. X-rays. X-rays are high energy, very small wavelength penetrating things between 0.1 nanometers and 10 nanometers. Because they're so small, they can go through most anything because the X-rays will go right through it. By the way, X-ray film is white. When the X-rays hit it, it turns black. So what you're seeing is the place where there's nothing there, it will appear black. Bones absorb all the X-rays. So that's why bones appear white, except for the joints, which are also black. And less dense tissue appears ghostly because the material is not absorbed. Also, X-rays have been used in more common times of being able to look inside different goods, and that's why here's a X-ray with a gun hidden at the bottom. Gamma radiation. Gamma radiation is the most powerful type of energy. It has a wavelength less than 1/1000th of a nanometer or a picometer. And the energy is so strong, it's going to cause an instant chemical reaction. Gamma radiation isn't really used outside of cancer treatment because it typically will cause damage and kill things it's attached to. However, it does have applications in science for being able to use light to cause chemical reactions. The eye. Our perception is based on our eyes. We have two parts of our eyes which see light, the rods and the cones. The rods just detect if there's any light there. The light enters our eye through the lens, and if it hits a rod, you can see something's there. That's, by the way, you can see rods very clearly if you turn out the lights in your room and it's dark and you can just see these faint little outlines of everything. That's rod vision. It's not very good, but it can help you bumble around in the dark. However, what you're experiencing is color vision. Most of your color vision is centered around the fovea, which is a whole bunch of the cones which can see color. By the way, I'd like you to note something. Please look at the picture of me in the camera. Stare for 3, 2, 1 seconds. Notice how blurry everything else is. That's because your vision is based on a tiny part of your eye called the fovea, which is very clear vision. That's full of cone cells in a very high density pattern, while everything else looks blurry and fuzzy because that's what the rest of your vision is like. Macula is the dense, high quality vision, and surrounding it is low quality vision. By the way, the reason you don't notice this is your brain fills in the gaps, and if you actually watch people's eyes, they're constantly scanning everything unless they're focused on something. White objects. White objects appear white because they have all the light that hits them bounce back at you. No light is absorbed. That's also why white is the coolest color, because if it's reflecting all of that light rather than absorbing it. Red objects are going to absorb all the light except for red, which it bounces back at you. What you're seeing is the color red because the light going into your eyes is red, while all the other colors are absorbing into it. Black objects absorb all the light. When you're seeing black, you are seeing all the light absorbs it. By the way, the most rich, deep black you can see is in the mirror. The pupil absorbs all the light going into the eye. Therefore, the black part of the eye, the pupil, absorbs all of the light. That's why it's so dark. Additive color. When you mix two colors together, they give you a different perception. Now, those of you in art class, hey, Dr. Melnizer, that's wrong. The additive colors are red, yellow, and blue. Well, we're broken. Human eyes don't see red, yellow, and blue. We see red, green, and blue. And that's why the colors match up like this for us. That's also why red, green, or red, blue, or blue, green are the types of color blindness we have because we have little defects in those types of cells. Now, light can be broken into different parts. Prisms break them apart by bending the light. I want to put that in a different place. Visible light is broken to the spectrum of 780 to 390 nanometers. The red at the largest, the violet at smallest. To put in perspective, that's about half of a millimeter, or approximately the thickness of 2 thumbnails. Optics. Optics is the branch of physics that talks about how light affects through different media. And there's 3 different ways we can affect light. We can reflect it, we can refract it, or we can diffract it. Reflection is something we've already talked about. Light bounces off something. When you see a color, you see light bounced off that object to you. That is reflection. Light, by the way, always bounces off at the same angle it impacts something at. Refraction. Now, sometimes light doesn't just reflect off something, it bends inside of it. This is usually happening as it's turning from one material to the other. In the case of a prism, it's going from the air to a solid. In the case of the picture here, a pencil sitting in a glass of water, it is bending. It looks like it's broken, but it's not. It's bending the light because it's changing from one speed to the other. That is because your perception is distorted because the light is bent. Refraction is the bending of light. Diffraction. Diffraction is the scattering of light, and the best example is when you're trying to sleep and someone turns on the light. If you're in a perfectly dark room and there is a tiny source of light and it spreads out to fill the entire room, that's diffraction. Best seen if you have a closed door and light in the next room, you'll see that little bit of light scatter and spread out on the opposing wall. That is diffraction. Light is going to travel through a small hole, and then it will bend and scatter to fill the area on the other side. It will not scatter evenly. It will create little slit patterns, but that concept of scattering of light is diffraction. Lastly, I want to talk about transparent, translucent versus opaque. When light is traveling through something, it can be affected in different ways. If all of the light is absorbed and we can't see through the other side, we call that opaque. Light can't travel through it. It is absorbed. If some of the light is absorbed or bent and we see something on the other side but it's distorted, we call that translucent. Whereas if we can see something clearly on the other side, that is transparent. Light is not significantly affected. All right. Thank you for your attention. I've posted our emails here. Thank you for your time today.